Hello again, ladies and gentlemen. Mr. Johnny here, looking at 16.6 stuff. Weak acids. So our objectives are to explain what makes a weak acid weak. Use Ka's to compare strengths of acid. Use Ka to calculate pH and concentrations, and vice versa for monoprotic and polyprotic acids, and calculate the percent ionization from pH. All right, so weak acids and bases, we've said this before, they don't completely ionize, right? Only partly dissociate in solution. So Ka is going to be the equilibrium expression for that weak acid. So weak acids, again, will only partially dissociate, right? So we got this equilibrium here with double-sided arrows. If HF is our example for a weak acid, it will dissociate partly by taking one of those H's and sending it over to the water, giving us H3O plus and F minus. So another way to write it is just showing the HF breaking up into H plus and F minus, right? So the Ka for that is going to be equivalent to the concentration of H plus times concentration of our anion divided by the original concentration of our weak acid. So Ka is just an equilibrium constant for an acid, right? Think A for acid. So comparing Ka's, if this is our expression for Ka, the greater the Ka is, the stronger the acid, because if we got a bigger Ka, that's because we have more H pluses, so it's going to be a stronger acid. I want you to pay attention to the scientific notation. Pay close attention to that. 1.0 times 10 to the minus 5 is a bigger number than 1.0 times 10 to the minus 6, right? 1.0 times 10 to the minus 5 is a bigger number than 4.5 times 10 to the minus 6. Don't let this part confuse you, all right? First, always look at the exponents. How do they compare? All right, 10 to the minus 5, bigger number than 10 to the minus 6. So look at the 10 to the first. So which is stronger, HF or acetic acid? Well, HF has a Ka of 6.8 times 10 to the minus 4, and acetic acid has a Ka of 1.8 times 10 to the minus 5. So the stronger acid is going to be HF because it has the bigger Ka. Notice here, I didn't even pay attention to the digits in front. I didn't even look at those because I didn't need to. All right, acetic acid with a Ka of 1.8 times 10 to the minus 5, or benzoic acid with a Ka of 6.3 times 10 to the minus 5. So in this one, they both have 10 to the minus 5. So now I'm going to look at the numbers in front. Well, 6.3 is bigger than 1.8, so benzoic acid is going to be our stronger acid. All right, benzoic acid, Ka of 6.3 times 10 to the minus 5, or nitrous acid, which has a Ka of 4.5 10 to the minus 4. So again, I'm going to look first at the exponents. Which one is bigger? 10 to the minus 4 is a bigger number than 10 to the minus 5. So that is going to be our stronger acid for that one. All right, so now let's take a look at calculating Ka's from pH, which is, you can also call it the return of the icebox problems, all right? So if we know the concentration of our solution and can measure the pH, we can calculate the Ka. So we know this is our generic expression for a weak acid, right? We have our weak acid, and it dissociates into H plus and the anion that it has. So Ka, generic expression would be this, H plus times the anion over Ha, the weak acid. So we can use the pH to determine the H plus concentration, which will also tell us the anion concentration, because if we're taking a look, for every one H plus we have to get one anion. So they're going to be equal concentrations. And the Ha is going to be the original concentration minus how much of it ionized, right? Because if I started with a certain amount of my acid, some of it broke down into its ions. So the original concentration minus how much of it broke down will give me the Ha for my Ka expression. All right, practice problem. A 0.1 molar solution of formic acid has a pH of 2.38 at a given temperature. Calculate the Ka. So first thing we want to do is we're going to want to use that pH to figure out the concentration of H+. So I know pH is equal to negative log of H+, which I can do some algebra, and I get H+ equals 10 to the negative pH. So I plug that in, and I get this number. That is my H+ concentration. So this is the reaction. I have formic acid. It breaks up into H+. and the formate ion. So initially I start with 0.1 molar of the formic acid and no H plus or the formate ion. Then it changes. How much did it change? Well, I figured that out with my pH calculation. I figured out the H plus concentration. So that's how much it changed. So for the original acid, that's how much got used up. So I want to subtract that from the original concentration. And for the H plus and the anion concentration, it went up that much. So at equilibrium, I have these values. Notice that my original weak acid concentration stayed the same because when I subtract this tiny, tiny number from 0.10 and I round to sig figs, I still get 0.10. So that kind of helps simplify things. So I got my Ka expression and I plug the numbers in, right? So H plus is 4.2 times 10 to the minus 3. Same thing for the anion, and I got to divide that all by the concentration of formic acid, which is at 0.10, and I get this as my Ka. And that's how you do those problems. Cool. What is the percent of the formic acid that ionized? So percent ionized, again, is going to be the amount that ionized divided by the original amount times 100. It's just a percent. So how much ionized? 4.2 times 10 to the minus 3. That's the H plus. That's how much broke apart over my original concentration of 0.10 molar and times it by 100%, and I get 4.2%. All right, calculating pH from Ka. So given Ka, what's the pH? If we know the Ka and we're given the initial concentration of an acid, we can calculate the pH by using an icebox. So first step, set up an icebox. Then use X for the change. We don't know what it is, we're going to figure it out. And then determine the equilibrium values. There's a 5% trick that we're going to talk about. You can assume that the initial minus your X is still equal to initial, like it did in the previous problem. But we have to remember to check to see that that assumption was a safe one to make. So we got to make sure that it was okay. We got to check. Then we solve for X, and you may need to use a quadratic equation for that. All right, so what is the pH of a 0.2 molar solution of HCN given this as the Ka? So HCN breaks apart into H plus and the cyanide ion, shown by that equation. So initially I start with 0.2 molar HCN and no H plus or Cn minus. It changes by amount X, right? HCN is going to go down X and the other ones are going to go up by a value of X. So at equilibrium, we're going to get 0.20 minus X and X and X for our values. We're going to try to make our lives a little bit easier, and we're going to assume that X is so small that when I do 0.20 minus X, which is my equilibrium concentration for the acid, that it still equals 0.20. We'll then have to check to see that our assumption is allowable. So we're going to assume that, and it simplifies to just X squared over 0.2 equals Ka. So then I solve for X. I get X equals 9.9 times 10 to the minus 6, and this is when I check. So now I'm going to plug that in. If I subtracted this from 0.20, will I still end up with 0.20? And when I round to sig figs, I sure do. So I just saved myself from having to use a quadratic equation. All right. If X is more than 5% of the initial value, then you can't use the assumption. If it's 5% or more, you got to actually use a quadratic equation. All right, so now I got my H plus concentration, and I know my formula for pH, and I just plug it in, and I get a pH of 5.0. So I've now finally answered my question. Next, I want to talk about polyprotic acids. So poly just means many, and protic means proton. So these are acids that have more than one proton to give off, right? So here's an example. This is H2SO4. It has 2 hydrogens that it can give up. All right, there's H3PO4, which would be a triprotic. H2SO4 is diprotic. All right, these prefixes probably aren't blowing your minds. So each proton will have its own K, its own equilibrium constant. Ka1 is for the first proton, Ka2 will be for the second one, and so on and so forth. So Ka1 is based on this equation. It's the first H that is given off. So the first H that gives off, we denote 1, right? And the second one, well, you're going to start, right? Slow it down. So ready? This is for Ka1, and then that would be for Ka2. And they dissociate to different extents. So Ka2 is going to be based on that second proton coming off. So we are going to start with HSO4 minus instead of H2SO4 because we had already gotten rid of one. So now that second hydrogen, what is the equilibrium constant for that one? Generally speaking, the first proton is the easiest one to remove. After you remove the first one, the second one will be removing a positive charge from something that is negatively charged. It's going to be more difficult. Sometimes you can ignore the second equilibrium constant. If Ka1 is much greater than Ka2, then the vast majority of H plus comes from the first proton and the rest can be ignored. So where's my pen? So if this happens a lot, and this one happens barely at all, we can ignore it and pretend it doesn't happen because it won't mess with our calculations. So when can you ignore it? Ka2. If Ka2 is less than Ka1 by a factor of 10 to the 3 or 1,000 times or greater, you can ignore it and treat it as if there was only one H+. You can ignore the fact that there's another one. Example, Ka1, 1.8 times 10 to the minus 5. If you had a Ka2 of 2.4 times 10 to the minus 9, you can see right there, hey, that's a difference of greater than 10 to the 3. So you can ignore this Ka2 and you just treat it as if it was monoprotic. It just had one proton. So ignore Ka2 and just use the first proton that comes off. All right, so I made this slide to try and show you why. So let's say I had a bunch of these H2SO4s, right? And the first Ka is pretty big. It is going to lose that first proton, and now I'm left with just sulfate ions with one proton. Only some of those protons are going to separate. So if we're looking at where did all of these protons come from, well, almost all of them are just from that first one. So we can ignore the fact that some of the second ones come off because there's barely any. All right, so what is the pH of a 0.0035 molar solution of H2SO3? And they give us the two Kas there. So because Ka1 is so much greater than Ka2, we can ignore the second one, right? 10 to the minus 2, 10 to the minus 8, that's a greater difference than 10 to the third. So we can ignore the second proton. All right, when we do our calculations, you can do the same thing that you would as if it was a monoprotic acid. All right, if it wasn't, you would then need to do two ice boxes to determine the total H plus concentration at equilibrium. Right, so you'd have to go, all right, H2SO3, first one pops off, use Ka1 to solve for how many H pluses you get, and then you've got to use Ka2 with this kind of equation. You go HSO3 minus, breaks off an H plus, give me H plus and SO3 minus 2, and then you got to use Ka2 to solve for this H plus from the second proton, and then you got to combine those two and use that as your concentration to determine the pH. That's everything. See you in class. Okay, bye.